Hello students. So today we will discuss about some important questions in the chapter haloalkanes and haloarenes, and the topic is nucleophilic substitution reaction. Okay, nucleophilic substitution reaction. Now the first question is, what is the first question? The order of reactivities of the following alkyl halides for a SN2 reaction. Now first of all, we know that always the primary alkyl halide favors the SN2 reaction. The order is primary, then secondary, then tertiary. But here in all the cases, the halide is your alkyl halide is primary alkyl halide. Now the difference is in the type of halogen groups, and we know that in between fluorine, chlorine, bromine and iodine, the best living group is your iodide, then bromide, then chloride, then fluoride. So according to that, we have to follow the order. So here in the option is D, where first is your methyl iodide, then methyl bromide, then methyl chloride, then methyl fluoride. So this is the order of reactivities of the corresponding alkyl halides for a SN2 reaction. D. Now the second question is the stereochemistry of the product formed if optically active alkyl halide undergoes substitution reaction by SN1 mechanism. That means, suppose for example, we will take one optically active halide. See here, for example, if you will take 2-bromobutane, this is your ethyl group, this is methyl, this is bromo. Okay, when we will proceed from this side, 1, 2, 3, 4. In 2 position there is a 2-bromobutane, and because all are 4 different groups, so it is an optically active alkyl halide. So when optically active halide, it is a what? It is a which type of compound? It is the secondary alkyl halide. Okay. Now first of all, when it undergoes dissociation, that is the slow step, it forms a carbocation. Here this one goes to this position, it becomes C plus carbocation, and it is known as a planar carbocation, and this is the halide and bromide ion, that is a living group. Now the question is, according to the question, what happens when there is a attack of different nucleophile occurs to the planar carbocation? Now see here what happens when the nucleophile will attack to the planar carbocation in the front side, then you will get a product that is known as butane 2OL, and here it is also 50% enantiomers. Okay. Similarly, when the nucleophile will attack the rear attack, that means the backside attack, then also a compound is formed, that is your butane 2OL. This is your dextro form, this is the livio form. Okay. So here also you will get the enantiomer, one is 50%. So if you will see, you will get a racemic mixture of the two products. Okay, so that means that the question, according to the question, the stereochemistry of the product formed if optically active alkyl halide undergoes substitution reaction after the formation of carbocation, there is a undergoes substitution reaction by SN1 mechanism is dash. So the answer is a racemic mixture. Okay, it is a racemic mixture, and the remaining region is due to the formation of the planar carbocation. That is why the answer will be racemic mixture. Okay. The next question is, third question, which is most reactive towards SN1 reaction? Which of the alkyl halide always favors SN1 reaction? We know that tertiary alkyl halide always favors SN1 reaction. Now in between this is ethyl primary alkyl halide, this is secondary alkyl halide, this is tertiary, this is also primary. So the answer is C. There is tertiary alkyl halide, that is tertiary butyl bromide is most reactive towards SN1 reaction. Okay. Now another important question is, out of these two, CH2 double bond CH3, what is the group? This is your allyl group. This is your allyl chloride. So out of allyl chloride, and this is your N-propyl chloride, CH3, CH2, CH2, Cl. So in between these two, your allyl chloride and N-propyl chloride, which one undergoes SN1 mechanism faster? Now actually, in between these two, always SN1 reaction gives faster is your allyl chloride. What is the reason behind it? This is an important question. The reason behind it is due to the formation of a carbocation. Suppose this is your allyl chloride. When there is a breaking of bond takes place, then this becomes your what? This bond goes to this position, and now this carbon possesses positive charge. So it is your allylic carbocation. Okay, and if you will see, there is a resonance hybridization takes place, resonance structure possible, because when this double bond goes to this position, there is a deficiency occurs here, so it is CH2 plus CH double bond CH2. So this is a allylic carbocation, and this is a regenerative structure. Two regenerative structures are possible. So that means the question, according to the question, out of these two, which one undergoes SN1 mechanism faster? Allylic chloride will go undergoes SN1 reaction faster? Because the main reason is the resonance stabilization of the allylic carbocation. Due to the resonance stabilization of the allylic carbocation, this answer is this one, undergoes your SN1 mechanism faster. Okay. Next question is, in the following pair of halogen compounds, which would undergo SN2 reaction? See here, this is a cyclohexane ring, CH2Cl. This is also cyclohexane ring, Cl. Now what is C here? If we will put a carbon here and you will satisfy this becomes what? CH. So this is your which carbon? This one is your secondary carbon, but the halogen which is attached to this carbon is a primary carbon, 1 degree carbon. But here in this compound, if we will put C here and will satisfy hydrogen, the halogen is chlorine is attached to which carbon atom? This is a secondary carbon atom. We know that if you compare between the primary halide and a secondary halide, which one undergoes SN2 reaction faster? Obviously, primary alkyl halide undergoes SN1 reaction faster. So due to the primary halide, due to this region, primary alkyl halide undergoes SN2 reaction faster. So the answer is this one. Okay. Now, next question is, compounds will react faster in SN1 reaction with OH minus ion. Now see here, one compound is your ethyl chloride and another compound is your benzyl chloride. Okay, see here, one is your ethyl chloride, another is benzyl chloride. Now in benzyl chloride, if you will see, this is benzyl chloride, this is your C6H5CH2, the benzyl group, chlorine attached to this, so it is a benzyl chloride. When it undergoes dissociation, here it forms what? It forms CH2 plus benzyl carbocation plus Cl minus. Okay, benzyl carbocation. Now in benzyl carbocation, there is a resonance stabilization takes place. Okay, so we'll draw the resonance structure. Now see, the resonance structure of this compound, this benzyl carbocation, see here, if we displace a bond to this position, okay, now there is a double bond occurs, this positive charge becomes satisfied, but there is a deficiency occurs here, so you will get a positive charge here, and this is the compound. If this one is your first compound, next resulting structure 2. Again what happens? Again the bond goes to this position, deficiency occurs here, here positive charge, and this is the structure, this is the third structure. Next, again this bond goes to this position, so deficiency occurs here, here there is a positive charge, so this is the fourth structure. So this resonating stabilization occurs in case of benzyl carbocation, but that doesn't happens in case of ethyl chloride. Here ethyl chloride does not undergo any ionization to give ethyl carbocation. It will not give ethyl carbocation, CH3CH2+. So that is the reason why, because of this resonance stabilization, your benzyl chloride undergo SN1 reaction faster with OH minus ion. Okay. Thank you.